Hello there. I am Paul Miles with the International Society for Biblical Hermeneutics, and I am here with Hannah Klein. Hannah is an author on the New Creation blog, and she is a physics student at the Liberty University. Today, she is speaking on her topic, Things Which Are Unseen, Dark Matter, and Creation Astronomy. Hannah, thank you so much for joining us. Take it away.
Thank you for having me, and thank you all for being here. So yeah, I'm Hannah Klein, and I'm a physics student at Liberty University, and I'm an author with the New Creation blog, like Paul just mentioned. We write about what's going on in creation science with an emphasis on positive creation model building and difficult questions in creation science, those kinds of things. So yes, and I'm going to be talking about dark matter and how it relates to creation astronomy. So what is dark matter? Dark matter is today it's thought to be a major constituent of the universe, and it's an entirely different form of matter that doesn't interact with electromagnetic radiation, doesn't interact with light at all. So that's why we call it dark matter. You can't see it or detect it at all by radiation, by electromagnetic radiation or by light. And it's thought to make up 85% of the universe, even though we don't know what it is. It makes up 85% of the matter in the universe. And it was first proposed in the 1930s. And it was proposed in response to this problem of missing mass, galaxies acting like they're heavier than they look. So it was the discovery of unusual motions in galaxies that led to the idea of dark matter. And so basically, dark matter is just it's a hypothetical new form of matter that we don't know, that doesn't fit at all in our it doesn't fit in our standard model of particle physics or anything like that. It's something completely different. And we don't know what it is, but it makes up most of the matter of the universe, is the idea. That's the hypothesis. So the evidence for dark matter, there's three main lines of evidence, and I'm going to go over two of them, and they all have to do with a discrepancy between what's called lighted mass and dynamic mass. So the way it works is there's two ways of measuring the mass of a galaxy. One is through lighted mass, which is the amount of mass that's needed to produce the light that we see from a given galaxy. Astronomers have a light to mass ratio by which you can determine the mass of a galaxy given its luminosity or its intrinsic brightness. And that's not just like how bright it looks like in a telescope, but it's measuring its intrinsic brightness, but taking into account its distance and things like that. And it's not just the visible light, but the electromagnetic radiation in general. That luminosity can be used to determine how much mass is in a galaxy. And then the other way of measuring the mass of a galaxy is by its dynamic mass, which is the amount of mass that's needed to account for the motion of a galaxy. So the way it works is that velocity is related to an object's mass. And so by measuring the galaxy's motion, its velocity, the way it rotates, the way it moves in a galaxy cluster, we can infer the mass of the galaxy. And so we would expect that the mass that we can infer based on its luminosity, the lighted mass of a galaxy, would give consistent results with the dynamic mass. They should give similar measurements. It's two different ways of measuring the same entity, the same property of the galaxy. And it turns out that that's not always the case, and that's where dark matter comes in. So in the case of galaxies, of spiral galaxies in particular, rotational speed within a galaxy is related to the mass of the galaxy and how that mass is distributed. So in the nucleus of a galaxy, we have a linear relationship between the rotational velocity and the mass. And so at any given point in the nucleus of the galaxy, the velocity is going to be dependent at that point on all the matter that's within that orbit at that point of the galaxy. And so as you move out from the center of the nucleus, as you move through the nucleus of the galaxy, the velocity increases linearly. And then it's expected that as you move to the outer regions of the galaxy, the outer arms where you see the dark spaces between the arms, the matter is not as densely distributed. At that point, it's expected that the velocity would drop off, because at that point in the galaxy, it's not behaving like a single object that's rotating. it's behaving more like the matter in the galaxy is, since it's more sparsely distributed, it's behaving more, it's expected to behave more like the planets in the solar system, more like independent objects that are moving around a central mass, center of gravity. And so the way this works is that we would expect that in the center of the galaxy, the nucleus, velocity increases with mass, or with distance, I should say. Velocity is increasing with mass and increasing with distance as you go from the center of the galaxy outward. But when you get to the outer regions of the galaxy, velocity should start to drop off, and it should start to follow the patterns that we see in the orbits, in the rotation speeds of the planets around the sun. So, and that's called Keplerian behavior. It's the outer edges of the galaxy are expected to behave kind of like the planets behave in the solar system, where there's an inverse relationship between distance from the center mass and the orbital velocity. So what this looks like, oops, I'm sorry, got my slides messed up there. So in the 1930s, astronomers began taking measurements of the radial velocity of galaxies at extreme edges. Earlier studies only focused on the nucleus of the galaxy because we didn't have the technology to get good measurements of the fainter light at the edges of the galaxies. But when they started being able to get measurements of velocities at the edges of galaxies, they found that the orbital velocity out at the edges of the galaxy was much higher than expected by the distribution of the light and mass, the visible mass of the galaxy. And so this is the Triangulum galaxy M33. And in the dashed gray line, you see that's the velocity that's expected from the visible disk. So we have velocity on the y-axis and distance on the x-axis here. And that gray dashed line shows how at the nucleus of the galaxy, we're expecting velocity to increase as we move out. And then once we get past the nucleus, the center localized portion of the galaxy where mass is more densely distributed, as we move to the arms of the galaxy where it's more sparse, the distribution of mass, we're expecting the velocity to drop off. And towards the right end of the graph there, that's the expected behavior, the expected velocity that we would see toward the outer edges of the galaxy. And that's including, as you can see, it extends beyond what you see in the picture as being the galaxy. There's matter in the galaxy that's so faint that it's not going to show up in this picture. That's why that graph extends so far to the right. The upper line there, the white solid line, that's the observations, that's the actual measured velocity that's been measured of the galaxy from starlight and other methods. And you can see that there's a very large discrepancy between how the galaxy actually is behaving, the velocity of the galaxy at its extreme edges, compared to what we expect based on the distribution of the light and mass, what we see of the galaxy. And so one astronomer in the 1940s that was writing about this phenomenon, he said that the distribution of mass in the system appears to bear almost no relation to the speed of light, to that of light. And the point being that the light that we see in the galaxy seems to have nothing to do whatsoever with how much mass is in the galaxy. They don't have any relationship at all. That's what it looks like based on how the galaxy is moving. So that's the first evidence for dark matter that was discovered in the 1930s, was galaxies moving in ways that doesn't make sense with how much mass they look like they have. They're acting like they're heavier than they look like they are. And then the second line of evidence for dark matter is from gravitational lensing. And gravitational lensing is when a massive object in space distorts the light from more distant objects behind it by its gravity. And this effect was, there's a notable experiment that demonstrates this effect in the 1919 total solar eclipse, where astronomers measured the apparent positions of stars in the vicinity of the sun during the solar eclipse, during totality, when the sun's surface is completely blocked, and so you can see the brighter stars. They measured the apparent positions of stars in the vicinity of the sun during that time, and then they compared that with star charts where the stars actually are, and they found that the stars' apparent position during the eclipse was actually different than where they actually are in space, because the sun's gravity was bending the paths of light from those stars. So that's what gravitational lensing, that's the kind of thing that gravitational lensing does. And I have an animation here. This is showing dark matter as the example, so that's why you don't see the mass in the center there. But it's showing the idea of how the gravity of a more massive object in between distorts the light of stars behind it. So the amount of distortion produced by an object allows us to calculate the mass of the object. So this is similar to the logic that was going on with spiral galaxies. By this time, instead of its velocity, we're looking at the amount of distortion it's producing on more distant objects behind it, the gravitational lensing that's occurring. And measurements of the masses of galaxy clusters by modeling the gravitational lensing they cause. That's shown a consistent discrepancy, again, between mass inferred from gravitational lensing and mass inferred from the luminosity of the galaxy cluster. So this picture is a good example of this phenomenon. So in this picture, the bright yellow objects in the photograph, those are members of a relatively nearby galaxy cluster, compared to compared to what's behind it, obviously, but the blue arcs that you see that kind of curve around the center of the photograph, those are gravitationally lensed images of more distant galaxies behind this cluster. And so astronomers can model the gravitational lensing that's going on in this cluster. And by doing that, they can infer how much mass should be in the galaxy cluster to create this much distortion. And it's been found that this, in cases like this, studies like this have shown that the total inferred mass is 5 to 10 times greater than the visible mass of the galaxy cluster. So in this case, we have this picture here. This next slide, this is a gravity map superimposed on that same photo. And this is showing the mass distribution that's required to produce the gravitational lensing that we're seeing in the photograph, which obviously this is much more dense than what we see in this photograph. So this is another case of missing mass. The galaxy cluster is acting like it's heavier than it looks. So those are the two main lines of evidence for dark matter, and they're showing just the general principle too. The general principle is just that the dynamic mass studies are showing that galaxies are denser than we are measuring through their luminosity, which implies that there's some sort of matter that's not giving off radiation that's making up a substantial amount of those galaxies. So I wanted to briefly mention a couple creation responses to dark matter. And so first off, one claim that gets made a lot by creationists is that dark matter is just a crutch for the Big Bang. It was just invented to salvage the Big Bang. So John Hartnett says that we need to understand that dark matter was, along with other unknowns, other model-driven assumptions, it was only proposed in the standard Big Bang cosmology to resolve some conflicts between the standard paradigm and astrophysical observations. So in other words, he's saying dark matter is just one of those things that the evolutionists just made up because the Big Bang model wasn't matching reality. And the fact is, evidence for dark matter was known before the Big Bang became the dominant cosmology. Around the time steady state theory was still in popularity, and back when dark matter was first proposed in the 1930s, the Big Bang theory didn't become widely accepted until the 60s. So dark matter predates the Big Bang chronologically. It doesn't make sense to say the Big Bang, the evolutionists invented dark matter to save the Big Bang, because dark matter was a concept before the Big Bang was really a dominant cosmology at all. And the other thing is that, like we just saw, the evidence for dark matter is independent of the Big Bang. All these things that we just talked about, this discrepancy between light and mass and dynamic mass and that kind of thing, that's all independent of Big Bang cosmology. We haven't referred to that once this whole time. It has nothing to do with the formation of the universe or things like that. Obviously, the Big Bang is going to incorporate dark matter into its cosmology, because that's what a cosmology does. It incorporates all the available evidence and observations about the universe. But it's not that dark matter was invented as a crutch from the Big Bang. It was actually independent altogether. And then another idea that goes around in some creation circles is that the problem isn't the data, the problem is our physics. And so one particular idea is that, well, we need to modify our understanding of physics. So some people suggest we use a modified form of Newtonian dynamics, which basically it does some tweaks on Newton's second law, and that's supposed to explain the discrepancy that we're seeing in mass distribution studies of galaxies. So the claim is that, well, this unexpected data isn't due to any form of matter. It's just a glitch in our physics. That's the idea. The problem is, if that's true, if the problem isn't that, if the problem is really just with our physics, then the discrepancy that we see that leads us, the lines of evidence that we see that make us think that dark matter is a thing, that should be consistent across all objects that we study. There should be a consistent discrepancy between dynamic and light and mass. It should be a systemic error. But in reality, not all galaxies have the same amount of dark matter. And some galaxies don't actually have any dark matter. So it turns out that in some cases, the absence of dark matter is actually strong evidence for it. It's not a consistent thing that all galaxies, given this luminosity, appear to have this much mass. And that's because we got something wrong with how we're measuring mass in a galaxy based on the dynamics of the galaxy. This is not, it's not a consistent discrepancy. Some galaxies have more, some have less, and some have none, which seems to imply that this is actually a case of there's a different type of matter out there that we need to reckon with. And the other thing is too that problems involving missing mass have a precedent in astronomy. So one example of that is Neptune, the discovery of Neptune. It was discovered because astronomers noticed things in the orbit of Uranus that didn't make sense with what was predicted by theory. And that got them thinking, perhaps there's something out there that's gravitationally affecting the orbit of Uranus and making it not match what we're expecting. There's some other mass out there. And that's how they discovered Neptune. And the same thing happened with some of Saturn's moons with interactions with the rings of Saturn. And there's other cases like that too. So it appears that, dark matter is just another one of these exciting discoveries that's waiting to happen. And of course, sometimes the problem there is we need to update our physics. There's cases like that as well in astronomy. But in this case, it does look like that the solution probably is a new form of matter that we haven't discovered yet. So how should we think about dark matter? First off, we should be scared away by the idea that dark matter is just a Big Bang concept. The two aren't very independent of each other. The evidence for dark matter is based on observational science. It's not a paradigm-based concept, and it's something that we need to fit into our models of creation astronomy, which, just like the Big Bang has been doing as well, they've been incorporating dark matter into their cosmology, using it to explain things, because that's what we have to, that's what you do with in a cosmology. You're trying to explain all the available data. So that's what we need to do in creation astronomy too, is we need to start figuring out how to explain this, how to make sense of this. But in conclusion, it's an exciting new frontier. It's exciting to find new things out there that we have no idea what they are, and they're just waiting. They're waiting to be discovered. As Proverbs 25:2 says, it's the glory of God to conceal a thing, and it's the glory of kings to search out the matter. And that's really exciting. So that concludes my presentation. I thank you kindly for your attention.
Thank you so much, Hannah. That was informative. I think we have a few minutes for a few questions. As of yet, you mentioned that this is something that we're still developing models for. Is there anything that could be indicating that dark matter could suggest an intelligent designer, or is it too early to tell?
Yeah. So there was one interesting creationist approach to dark matter that's been published it was published in the creationist literature, and I didn't have time to mention this here, but there's an idea that perhaps what we're seeing as dark matter is actually related to the inherent structure of space, and perhaps this is actually pointing us to the way that God designed the universe. Perhaps it's actually pointing to intentional design structure in the universe. So that's an interesting idea that's being developed by some creationist physicists.
Okay.
So yeah, but I mean, it is kind of early, so yeah.
That's very exciting. It's fun to see the early stages of something that's developing, not quite knowing which way it's going to go yet.
Yeah.
All right. Well, thank you so much. This has been Hannah Klein, author on the New Creation blog, available at www.newcreation.blog. If you're interested in reading that, they've got all sorts of cool articles on there. Hannah, thank you so much. I appreciate you.
Thank you.